Hello everyone and welcome to another video. So today I'd like to continue our discussion on numerical optimization algorithms, and in particular I want to investigate using what's known as the Armijo rule for choosing the step size. Now remember, we've talked extensively about step size selection in your numerical optimization routine. In fact, we've had multiple videos on that in the past. So if you haven't seen these two videos before, please make sure you watch those before continuing on, because I want to directly extend some of these ideas. And in fact, we're going to continue working with one of the cost functions that we looked at in the line minimization video. So in particular, maybe just to set the stage for why we want the Armijo rule and why it's useful, let me draw your attention back to the cost function that we examined, like I mentioned in the previous line minimization discussion. So if you remember, in the way of choosing the step size using the line minimization technique, we said, okay, if you are sitting at some location, X in state space or decision space, and you've chosen your descent direction, which we called D0 or DK or whatever, right? The way line minimization worked, right, is that it said, well, I'm just going to go ahead and look along this line from 0 to infinity, and I'll find the minimum location of the cost function, and that's going to be my step size, right? And again, that made perfectly good sense theoretically, right? And conceptually, that was a great way to go about it. But we saw that practically, the way that you're going to do this is you're going to take this search direction, and you're going to chop this up into, you know, hundreds or thousands of points, right? And you're going to look along this line for, I don't know, 2,000, 3,000, 10,000 locations, and you're going to iteratively evaluate the cost function at every single one of these blue dots, and then find the minimum, right? That's how you're going to numerically implement this in MATLAB, C, whatever, right? Now, that again is all fine and dandy, especially it's fine and dandy if you happen to have an analytical or an easily evaluatable version of your cost function, right? Remember, this was the cost function we were dealing with, and again, it's nothing super complicated, but again, think about this from another perspective. What if you didn't have this cost function available, right? What if this was hidden from you, or maybe even in another, maybe more real world situation, you have some unknown black box for your cost function, right? You might not even have an analytical description of it. This might be some, a flight simulator where you stick in some state vector or some decision vector, and out comes the cost at that location, right? So you don't even have an analytical description of this. And what's more concerning is, yeah, if this is really complicated, this cost function, like it's an entire flight simulator, like doing one run of this means booting up the flight simulator, flying a mission, and then evaluating the cost. Evaluating the cost function even one single time might be computationally expensive, right? So this approach of doing this 5,000 times is no longer tractable, right? It's not practical. So what the Armijo rule does is, the Armijo rule is similar to this line search, but it asks the question of, instead of brute forcing this by discretizing this search direction into thousands of locations, could I maybe identify certain ones of these which matter more than others? Can I maybe take a step, like maybe I'll test out here, and if that doesn't go so well, maybe I'll test some other location or another location, and maybe only have to do this 4, 5, maybe 10 times along this direction, and still be able to find a step size which makes the cost function go down and actually provides some guarantees, right? So that's what the Armijo rule is going to buy us. It's going to buy us a very similar type of behavior as the line search or the line minimization, but it's going to do so at a much more favorable computational cost. Okay, so if that sounds good, maybe let's talk about what is the Armijo rule. And what's really cool about the Armijo rule is it's fairly simple to implement, and there aren't too many parameters associated with it. In fact, there's only really 3 parameters associated with the Armijo rule. So the first parameter is a value of s, and the only restriction on s is that this has to be greater than 0, okay? The other parameter is another parameter which is beta, okay? And the restriction of this is beta needs to be in the range of 0 to 1 exclusive, right? So in other words, beta has to be, whoops, sorry, ran out of space. Beta has to be strictly greater than 0 and strictly less than 1. You can't have a beta of 0 and you can't have a beta of 1, but anything in between is fine, okay? And then finally, you have another parameter known as sigma, okay? And same thing, sigma, whoops, needs to be in the range of 0 to 1 exclusive as well, okay? So that's the idea. It's these parameters, okay? And now, once you have these three parameters, the step size that you're interested in is really easy. So the step size is simply going to be alpha k, right, which is your step size. It's just going to be beta to the mk times s. Okay? And here, this parameter, this mk, is basically, this is the first non-negative integer for which the following is true, okay? So f of xk is greater than or equal to f of xk plus beta to the ms dk minus sigma times beta to the ms gradient of f of xk transpose times dk. Okay, this looks like a mouthful, and in fact, this is quite a bit. I bet let's label this equation. Let's call this in the notes. I have this as equation 5. So let's be consistent. Okay, so this looks like a lot, but we're actually going to see this is actually pretty slick, and it's not that bad. So again, you just choose these three parameters, s, beta, and sigma. Those are the inputs to this algorithm, right? You basically pick them at the start, and again, we're going to talk about what these physically mean in a second, but for now, just imagine these are given to you, right? And then, it's actually really easy. The step size is, you just take beta to the mk times s. That gives you your step size. The only thing that's interesting is this mk. So what mk is you start at 0, right? It's the first non-negative integer. So you start at m equals 0 and you check, does it satisfy this equation? And again, look at this. You know all these terms. You can evaluate the cost function where you are. Then you know what beta is, you know what m is, right? M starts at 0, then it goes to 1, 2, 3, 4, whatever, right? You know what dk is, right? You already have picked your descent direction in this algorithm. You know what sigma is, you know everything. You know what the gradient of the cost function is at a current location. So again, this might look like a mouthful, but it's one simple check in an if statement, right? You check, does m equals 0 satisfy this? If no, you bump up m, go m equals 1. Check, does it satisfy it? No. Go to m equals 2, etc., etc., and eventually we're going to see that this should satisfy at some number beta, right? This should become true. That's when you break out of this and you just calculate your step size right off the bat. So, in fact, why don't we let's write this up as some pseudo code, because as you can see, it's actually just going to be a few lines. So let me erase some of this just to get ourselves some room. So pseudocode for this, for maybe let's call this, an Armijo rule. This is the name of our function, right? So to use MATLAB speak, you know what we should do instead? Let me just prototype this up like a MATLAB function, right? So you're gonna have something, function. The whole deal with Armijo rule is it's going to spit out alpha k, right? That's all this thing is going to do, right? And apparently, all you're going to need to tell the Armijo rule is you need to tell it the descent direction. So it needs to know where you're going, dk. What else do we need to tell it? We need to tell it the three parameters, s, beta, and sigma. And that's pretty much it. I'll assume that you also, this Armijo rule has access to the cost function, has access to the cost function gradient. Heck, maybe you want to you know, pass in the gradient of the cost function in as a parameter. But again, we'll look at this in actual code in a second. But you know, from a high level perspective, this is what it needs to know: the descent direction, the 3 parameters, and it will calculate the step size alpha k using this scheme. So it's really easy. Let's go ahead, and now that you have all these, let's just talk about this. So again, let's put a comment here, and we'll note that S, beta, and sigma are given / known. Right, and I guess so is dk. All right, so all you got to do is in this pseudocode, we're going to initialize m. M is going to be 0, right? Start this out as m equals 0, and then all we're going to do is let's just start some while one loop. Right, and this is pretty simple. While one, I'm going to put an end statement down here. Okay, so in this loop, all you're doing is literally you're just checking is this thing true, right? So just check, you know, if this thing is true. Maybe I'll just write this in to be lazy. I'm just going to say, is equation 5 true, right? If it is, you're basically done, right? So what you're going to do is just, I don't know, let's call mk. This is the critical thing we want. It's just the current value of m, right? And then you're going to break yourself out of this loop, right? So exit the loop. If it's not true, right, all you're going to do is just basically, what? You're just going to increment m, right? So this is really dumb. M is m plus 1, right? And then I'll end the if statement, and then I'll end the while one loop. Okay, so by the time we exit out of this while one loop, we have got our mk defined. So now it's just a matter of calculate alpha k, right? So outside here, the next line, oh shucks, I'm going to run out of space. Let me do this. Okay, so now you have enough information to basically say alpha k, whoops, alpha, I want alpha, not a. Alpha k, it's nothing more than beta to the mk times s. That's the return argument, and then you're done, right? So it's not that bad. So you can pretty much code this up in just a few lines, okay? Now, while it's easy to implement, we should ask ourselves, what is going on with the Armijo rule? Why does this work? We should do a little bit of analysis on what is this little check that we're doing here. We're gonna see that a lot of it comes down to what's going on when we're testing this. So tell you what, give me a second to erase the board, and we'll analyze this in just a second. All right, so I moved some of the important relationships up to this section of the board to kind of get out of the way. So again, remember, these are the 3 parameters of the Armijo rule, and then this is how we are choosing the step size. And then here was that interesting check that we need to perform at each step of the, each sub-step, I should say, within the Armijo rule function, right? So let's make a couple of observations, and we'll understand what the Armijo rule is doing, I think, by digging a little bit deeper into this. So a couple of things to note. Right off the bat, we can obviously see that beta, actually in fact, S, beta, and sigma, all of those are positive numbers, right? There's no way they can be 0 or negative, okay? So in conjunction with that, actually, if you look at this, then one other thing that we can note is that beta to the m, right? This is also strictly positive, right? We can see that because beta is always positive and m, it starts at 0 and then goes only up, right? It's integer values going up. So this is always also going to be positive, right? So using these observations, what we can do is actually make a note that this entire second term, including the minus sign, so maybe let me be very careful where I'm drawing these braces. This entire second term in the Armijo rule, this thing, if you look at it, let's think of it, see if we can tease this out, right? Maybe we should make a note here. Let's make a couple of notes, right? We also note, right, well, what do we know about dk, right? This thing was a descent direction, right? So what is the property of a descent direction? The descent direction meant that when you take the gradient of the cost function at a location, right, dotted with the direction that you're going, right, this is going to be strictly negative, right? That's the whole definition of a descent direction. If you move in this direction, the directional derivative of the function in that direction is negative, meaning the cost function will immediately go down in the vicinity of xk, right, if you move in the direction dk. So we can see that this term term right here is negative, right? Maybe let me see how many colors we can jam into here, right? The gradient FK transpose DK, this is negative. I'll just write this as negative. Right? That's negative. Okay, what do we just say about beta? Beta to the m, this term right here, this is positive, right? This beta to the m, this is positive, right? What about sigma? We know sigma here, this is positive. And then you got a negative term here, right? You got this minus sign. Obviously, the minus sign is negative, right? So look at this. This entire thing, you get a negative, positive, positive, negative. So this thing that we've got here in green, this has to be positive, right? This whole thing is positive,
So what is that?
right? In fact, why don't we call this entire thing, let's call this the improvement factor, okay? Maybe where should I put that? Let's define this down here. So let's go ahead and arbitrarily, I'm going to define or rename, I guess, maybe is a better way to put this. We're just going to rename this entire gobbledygook there, including the negative sign, as the improvement factor, or I'll abbreviate this as IF, right? So the improvement factor at any given step is negative sigma beta to the m s grad f xk transpose dotted with dk, okay? And also the other thing to note about this, look at this, sigma, this is constant, doesn't change, beta is constant, s is constant, the gradient is constant because our xk at a given location is constant, right? We're all thinking about what does this look like at a given location xk, and same thing, dk is constant, but beta can, or m can potentially change, right? So maybe to denote that, I'm going to say this improvement factor is a function of m, right? So again, you start at m equals 0, you check if that thing is true, if not, m becomes 1, check if it's true, if not, m becomes 2, etc., etc. So this improvement factor changes with every iteration, right? So what's interesting is, again, stare at this thing long enough. We just showed that this must be positive, right? So maybe let's again make a note here. Let's make a couple of bullets, right? So the improvement factor of m is strictly positive for all values of m, right? Again, I guess maybe we should say for all m that we're considering, right? The ones that are in the positive integers. Or I guess we should even say non-negative integers, right? That's the ones where, let's just say m is in 0, 1, 2, etc., etc., right? Non-negative integers, right? So the improvement factor has to be positive. And what's also interesting is if you look at how this improvement factor operates, right? Again, because beta is in the range of 0 to the 1, right? So when m is equal to 0, you basically just have beta. When m becomes 1, sorry, no, when m is 0, this is 1, right? I guess what I'm getting at is beta to the m, right? What does this thing look like versus m? Right, if we just make a table. So when m is 0, this thing is 1, right? When this thing is 1, this thing is what? It's just beta. When m is 2, you get beta squared, right? Yada, yada, yada. 3, you get beta cubed, right? Now, the thing to note, though, is because beta is strictly less than 1, right? This whole thing is getting smaller and smaller and smaller and smaller, right? Beta to the m becomes smaller and smaller and smaller, right? So numerically, I don't know, let's make something up. Let's say beta is 0.8, right? So this would just be 0.8, right? And then beta squared is 0.8 times 0.8, so what is that, 0.64 or something like that? Then you got 0.8 times 0.8 times 0.8. Does everyone see what this is, what we are getting at here? What I'm getting at is I want to make a note here that as m increases, right, the whole improvement factor, right, m decreases. Again, and the reason that happens is because this beta to the m term, this is the only thing that's changing at every location. Everything else in this term is fixed and constant. So the entire improvement factor, as m goes up, im just starts going down. Maybe let's use arrows. right? So we know the improvement factor is always greater than 0, and as you keep cranking m up, this improvement factor goes down and down and down and down and down, right? Okay, so if we accept all this, let's just go ahead and rewrite this entire check, right? That complicated check statement that we had here, right? We are checking to see if f of xk is greater than or equal to f of xk plus beta to the m s dk, right? Then what we can do is I can just write this now as plus the improvement factor at m, or sub m, right? Okay, cool. Let's keep going. Let's make a note, right? Do you recall the whole idea with our numerical optimization routine, right, was we said that okay, the step size here was beta to the m times s, right? So a candidate alpha, right? It's not alpha k. Alpha k is the actual step size we're going to take. But, you know, we're checking it every time. Does alpha of beta to the m times s, does that work, right? So let me just plug this in, right? This is really how we are choosing a step size at any sub-iteration of the Armijo rule. We're just asking, does this step size effectively work, right? That's the step size of beta to the m to the times s, right? So that's this thing right here. So look at this. You can rewrite this whole thing. Left-hand side is the same, greater than or equal to f of xk plus alpha dk, right? Plus the improvement factor. Oops, if. So to the m, right? Okay, now again, this is exactly, you know, if alpha is your candidate step size, you take that step size in the direction dk and you move that distance away from where you are right now. This entire thing in parentheses, this is your potential candidate x of k plus 1, right? That's where we're going. So you're asking yourself, does where I'm going to go, if I take a step size of this alpha, does it satisfy this entire relationship, right? So again, I can write this as f of xk greater than or equal to f of xk plus 1 plus the improvement factor sub n, right? So what's great about this is you can immediately see where this crazy wonky check came from. All this is doing, right, is the Armijo rule is going to pick a step size alpha that is going to guarantee that the cost function value at the new location is less than where you are by the improvement factor, right? So let's back this up and parse that again, right? If you stare at this long enough, right? If, for example, let's say that the current cost function location of where you're sitting right now, right? That's this location. Here's your current guess, right? And I'm going to make up some number. Let's say this is 10.5. Right? That's the cost function value, right? And now your improvement factor, you know, at a given m, right? So again, remember the improvement factor, where was it? Down here. This thing, right? You know all of these. So for whatever value of s, beta, sigma you've gone ahead and chosen, you plug it all into here and you figure out what's your improvement factor at m equals 0, right? And let's say your improvement factor comes out to be, you know, 2.5, something like that, right? So what the Armijo rule is going to do is it's going to check to see if I take a step size in the direction dk by this distance, does this cost function value, this had better be, in order to make this true, this has to be what? It has to be what, gosh, can I do the math? 8, right? Yeah, 8 or less, right? In order to make this inequality true. So if the cost function value at this new stepped location, like for example right here, right? This is your candidate location. So this is your test distance alpha is equal to beta to the ms, right? If this spot, if the cost function here is 8 or less, thumbs up. Armijo rule says you're good, you're done, you can exit, and that's the step you're going to take, right? Because it is shown that the cost function, you'll guarantee that the cost function value has decreased by at least the improvement factor. Now, if it's not true, right? What if this thing, if the cost function value here was, 9, right? So even though we see that the cost function value went down by moving to this location, right? It used to be 10.5, it went down to 9, but the improvement factor, it didn't achieve the appropriate improvement factor, right? So in that case, what we need to do is we need to go through the Armijo rule again. We're going to increment m by 1, and you're going to see, as we discussed, that is going to make the improvement factor go down, right? So it will become smaller. So you're not going to demand as much improvement at the next sub iteration. So this might come down to, I don't know, I'm going to make up another number, right? It might come down to 1.5 or something like that. And then that is going to change the step size location, and then that's going to therefore change the potential cost function value, and maybe now this is like 7 or something like that. And now you're hunky-dory. So again, sorry, that might be a little more confusing. We're going to look at an explicit example of running through this, but I'm hopefully now we're getting a feel for what these different parameters are doing, right? So, in fact, to get a better idea of that, all right, yeah, let's rewrite this. So let me move this to the other side. So we can write this as f of xk minus f of xk plus 1. It's got to be greater than or equal to the improvement factor sub m. Okay, so let's go ahead and resubstitute. Actually, we'll go back to this form, right? We said x of k plus 1 is nothing more than f of xk plus alpha dk, right? So this is now f of xk minus f of xk plus alpha dk, right, is less than, or sorry, greater than or equal to the improvement factor, which again, let's substitute in the definition of the improvement factor, right? This was negative sigma beta to the ms grad f of xk transpose dk, right? Okay, and then let's go ahead and make the note that this term right here, this beta to the ms, that's nothing more than the candidate step size that we're interested in, right? So it's alpha, right? So this alpha is the same as that alpha, right? It's again, it's at each sub-step of the Armijo rule, inside that while loop, what is the potential candidate alpha that you'd like to test to see if it satisfies this relationship or not? Okay, so with that, I think we can write this whole thing as f of xk minus f of xk plus alpha dk. All right, it's got to be greater than or equal to, and in fact, I'm going to pull the alpha out to the other side. So this is, let me see, minus sigma grad, oops, let me make this more explicit. My sigmas look kind of like gradients. Gradient f of xk transpose dk. Yeah, I think that's it, right, times alpha. All right, and then to get rid of this negative sign, let's just go ahead and flip the orders. So I guess we can write this whole thing as f of xk plus alpha dk, all right, minus f of xk has got to be less than or equal to, right, because again, I'm multiplying both sides by a -1, so I got to flip the inequality. So this becomes, what, sigma grad f of xk transpose dk. Again, I'll put this in brackets, I guess, just to denote that this is a quantity. Okay, there we go. Okay, so if you look at this thing, what you can see is, let's look at the left-hand side. So this is just some constant, right? This is just some offset, right? Or a constant, if you want to think about it that way from a graphing perspective. I basically want to look at this as y is equal to mx, right? This whole thing looks a little bit like, I want the whole left-hand side to basically be a y is equal to, here is some slope m times your independent variable x, right? So this is basically the equation of a line going through the origin. If I plot this entire quantity on the y-axis, this is the slope, here's an alpha on the x-axis, right? So again, if you look at this, this is basically, this left-hand side is how much did the cost function change from the cost function value at xk, right? So this is, again, how much did the cost function change if you were to take a step of size alpha, right? And then over here, this entire thing, here's the slope times alpha. So again, what I'm going to want to plot is we want to make some kind of plot where you have alpha on the x-axis, and on the y-axis, I'm going to draw it like this. This y-axis is f of xk plus alpha dk, right, minus f of xk. Right? Now, the question is, what does this line look like, right? We see it's a line. We see it's got to go through the origin, right? Now the question is, which direction does this line go? Again, remember that this term here, this grad f of xk transpose times dk, the whole deal was dk was a descent direction, right? So I know that that term is going to be negative, right? And we know that this sigma, again, the way it was chosen is between the range of 0 and 1, so it's positive. So in other words, this slope has to be negative. So this line is going to look like this, right? This is going to be the line sigma times grad f of xk transpose dk times alpha, right? So this green line is a straight line with this slope, okay? Now, we got to ask ourselves, what is this going to look like, right? This term, if you think about this long enough, again, this is almost exactly the picture that we examined when we were talking about line minimization. This is asking, how does the cost function change as you move along a line starting at xk, right, at this black dot here, you move in the direction dk, which is this sort of dashed blue green dotted line, right, and you move along in the distance alpha. So all this is basically, what does the cost function value look like as you start going along the line dk, and then we're just going to offset it by its current location. So it's basically, it's the cost function value, but it starts at 0, right? So again, remember, I'm going to assume you watched the previous video on the line minimization, right? It looks like, I don't know, maybe this thing goes, you know, how should we write this? You know, maybe I should have used a different color. Let me use a different color. Let me use blue. Okay. So, you know, I don't know, it does something like, I don't know, again, I'm making this up, right? So this blue line is this term over here, right? So the blue is f of xk plus alpha dk minus f of xk, right? Okay, so now we can actually graphically see where does this satisfy, right? So what you're asking for, what the Armijo rule is checking, is basically where does the blue line, in this case, fall underneath the green line, right? So if you look at this, you see that, you know, in here, you know, from here to here, right? You see this window, the blue line is below the green line. So this would be an acceptable alpha choice, right? The Armijo rule, if you happen to choose an alpha in this range, that is, yay, thumbs up, it should exit out of the while one loop that we defined earlier. Similarly, over here, it looks like, to here, this is also acceptable. Alpha choices, right? Whereas these regions are no good, right? So I'm gonna maybe mark this as X's as bad, 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 bad. Maybe I should use a different color, but hopefully graphically you see what's going on, right? Now, again, look at this. Let's ask ourselves, how does this green line can we tune the green line, right? And again, yes, you see that the way the green line is, its slope is like this. So we got to ask ourselves, what tuning knobs or what control authority do we have on this? Well, DK is fixed, right? We know which direction we're heading. The gradient is fixed. We know what we're doing, what the gradient looks like at xk. We can't change it. So sigma, we actually see sigma will directly tune how steep or shallow this green line is, right? So again, you notice that the way we've defined sigma is between 0 and 1, right? So almost the worst case scenario is a sigma of 1. In that sense, what happens if sigma is 1? If sigma is 1, this whole thing becomes, the slope is the gradient times dk. So actually, what do we end up with? If that's the case, we end up with this line, right? That it should go tangent to basically this right at the start. Geez, I don't know if I'm drawing this entirely accurately. So this is the sigma equals 1 line, right? And since we can't actually make sigma equal to 1, right? Sigma has to be slightly less than 1. So really this line should be slightly that direction, right? But again, I can't infinitesimally draw it that way. But I guess this is an interesting thought experiment for you as the viewer. What does this look like right here in the neighborhood of alpha equals 0? Well, because if you think about this, since this is, the sigma equals 1 line is tangent to the blue, right, at the origin, the sigma which is slightly less than 1, right, the sigma of less than 1, right, that's going to actually, I think if you were to zoom in on this picture right here, right, you would see the blue, when you see, I guess the green line here, here's the sigma of less than 1 line, and the blue line, it should probably go under it ever so slightly, right? Basically, what this is telling us is that if you choose sigma small enough, there is an area, or sorry, if you choose alpha small enough, eventually you can get to the red, the blue line going underneath the green line, and the Armijo rule should satisfy. So again, that's really kind of interesting that this almost has a baked-in protection that if alpha is small enough, right, then Armijo should exit. Right? So you're never going to get stuck in that while one loop. It should hopefully exit because you'll eventually start choosing the alpha values small enough that you get close enough to the origin that it has this behavior, right? So again, you can also see that the way alpha is being chosen, right, is as m starts going up and up and up, right, no matter what s value you have, eventually this term beta to the m is going to become 0, right? So this converges to 0, therefore alpha starts converging to 0, therefore you start moving closer to this unavoidable situation where it should exit. So again, hopefully that puts some of your mind to rest that, you know, whenever I write a while one loop, I always have to ask myself, is there ever a situation where I'm going to get stuck in an infinite loop? And hopefully this analysis convinces you that, no, that shouldn't happen with the Armijo rule if it's coded up appropriately, right? Okay, so now, this is great because now we can see what all of these parameters do. So for example, this sigma value, right? We now can write, and we understand that this sigma, this is sort of like telling us how much improvement do we demand at each iteration of the Armijo rule, right? So let's write that down. So this basically helps us describe how much improvement do we demand at each step of the Armijo rule, right? And actually here, let me erase some of these things so we have some more room to write. Okay? Because we see that basically sigma is going to tune the slope of this green curve, right? So if the green curve is not so steep, right, if it's closer to 0, the Armijo rule will basically exit even though the improvement factor is not so high, right? So basically, it will allow you to choose step sizes where the cost function doesn't improve that much. So this is almost like tuning how aggressive or how much, yeah, I mean, how much improvement are we asking for each step of the Armijo rule, right? So we can see that basically closer to 1, what does that mean? This basically means you want it more aggressive, right? Right, so this is almost like, you can think about this as more aggressive improvements, right? Because then you're getting closer to this situation where you need a lot of improvement, right? Whereas closer to 0 means the slope of this line is much flatter, right? So in that case, I guess this is less aggressive improvements, right? Okay. Okay. What else? What are these other ones? How about beta? Let's do this in another color so I don't all run into each other. So beta, you can actually see right here. Here's how beta works its way into it, and this tells you what does beta tune in terms of your algorithm. So beta, you can see, basically tells us how much does the candidate step size change with each sub-iteration of the Armijo rule, right? So a beta closer to 1 means that actually the step sizes are not going to change very much, right? You can clearly see that, right? If beta is closer to 1, beta to the m, it doesn't change as much with each m iteration, right? So again, let's write this down. So beta, this is basically telling us how aggressive is changes in alpha with each step. Or I guess we should call it, again, sub-step of the Armijo rule, right? So again, we see that closer to 1, this means less change. And then closer to 0 means more change. So again, coming over to this picture, what's going to end up happening, right, is say you go through your Armijo rule with whatever constants, and the first step size you chose ends up here, right? This is in the unacceptable range, right, with all of these x's. So the Armijo rule is going to say, no, that value of m equals 0, let's say this is the m equals 0 iteration, right? That's your candidate step size. If that doesn't work, you're going to bump up m to 1, and we're going to ask ourselves, how does it change? Well, depending on your value of beta, this might change a little bit, like here. It just might make these small steps, and then hopefully you end up in here. So small steps, again, correspond to beta values which are closer to 1. Or you could have large steps, right? So instead of these small little dinky steps, you might take large steps. But here's what's actually interesting. The larger step you take, you notice that we jumped over completely this acceptable range, and we ended up into an unacceptable range. And then it will go again, right? And again, you're going to see this. We'll run this in MATLAB just so you can get a better feel for them. But again, this is what beta is doing. So beta is tuning your step size. Sigma is tuning your amount of improvement, or basically the slope of this green line, right? And then finally, let's ask ourselves, what is S, right? And again, you can see it. Here's S right away. And actually, you can see, remember, the Armijo rule starts out with m equals 0, right? So really, the Armijo rule, the first candidate alpha that it chooses is beta to the 0 times s, or alpha is equal to s, right? So actually, you can see right off the bat, S is the maximum step size that you want to start the Armijo rule algorithm at, right? So S is, again, let's write that down just so we're all on the same page. This is the maximum alpha value to consider in the Armijo rule. So again, coming to our picture here, right? If we knew that I want to only look for step sizes, you know, within the range of, say, 0 to 8 or something like that. Let's say this is where 8 alpha is equal to 8 kind of corresponds. I don't really need to calculate or consider cases of alpha all the way out to infinity. Let's just cap it at 8. So in that case, I would choose s is equal to 8 in my algorithm, right? So I think we've analyzed this thing to death. Maybe what we should do is we should maybe jump over to MATLAB. Let's code all this up for this exact problem and go ahead and let the Armijo rule rip and see what it comes up with. One thing I probably should mention, and I just realized that I probably should have mentioned this actually in the last discussion when we were talking about line minimization. I forgot to characterize all of these stationary points. So I think I kind of stated without proof that this was sort of the global minima we were kind of gunning for. Well, there's actually multiple stationary points and several local minima throughout this cost function in these areas. Let me clean this picture up, maybe to make this not so cluttered. I'll try to clean this up as best as I can without erasing too much. Okay. Right, so these red dot locations are actually the stationary points of this problem, and if you were to evaluate the cost function at these locations, this one here has a cost function value of 60. These two have a cost function value of 42.5-ish. And then these cost functions values have values of 36.4, J of 36.4. So indeed, this one here, right, is one that you can go for, or this is the other one, right? So ideally, those are the global minima of this cost function. All these other ones are local minima. But again, like I said, I think I stated that without proof. So again, if you're interested in these actual locations, feel free to check out the notes. But again, this is what we're hoping the algorithm gets us to this bottom location from one of these starting points. So, all right. I think that's enough preamble. Why don't we jump over to MATLAB and take a look at this and see if this works. All right, so here we are in MATLAB, and let's basically code up one iteration of the Armijo rule. And again, let's use the exact same scenario that we did when we previously examined the line minimization technique for choosing the step size. So for this first scenario, again, like we said, we're going to choose the exact same starting location. And now let's choose an S of 15. So remember, that's our initial maximum step size that we're going to consider. And again, we'll choose, reasonable values for sigma and beta. So again, sigma is 0.15, so it's not anywhere near 1. So we're basically saying we don't demand a lot of improvement with each iteration. And beta is actually closer to 1. So we're basically saying take small incremental changes in the step size for each sub-iteration of the Armijo rule. So again, there's a lot of code here, but most of this is just plotting. Let me scroll down to the actual guts of the Armijo rule, and here it is. And as you can see, it's basically like what we talked about on the board, right? You just basically set the integer m to 0, when you just drop into this while one loop, and then we're just going to consider, here's the candidate alpha solution. It's just beta to the m times s, and then all we're going to do is we're going to look at where are we going to go, x of k plus 1, if we chose that candidate step size and the associated direction, and then basically we're just going to check, does the cost function value at that point decrease from the previous value by the specified improvement factor, and if so, we are going to then use that step size as our that candidate step size as the actual step size for this iteration and break out of the loop, and we're basically done. If not, we basically just increment m by 1 and run through this again. So let's go ahead and run this, and we can take a look at what it looks like. So again, just for giggles, I'll show you, here is the picture that goes along with it, right? Here's our initial guess location. We're searching along this direction for maximum of 15 units, and we're just calculating the Armijo rule. And here, let me pull up what it looks like. This is what the algorithm looks like. So let me get this legend out of the way so we can kind of see what's going on. So again, the blue line is, as we discussed, this is the cost function value minus the initial cost function value. So again, you can think of it as just an offset version of what the cost function looks like along this green line. right? And then as you can see, I've drawn here in magenta, this is the line of basically that improvement factor if you had an alpha of exactly, or excuse me, if you had a sigma of exactly equal to 1. So this is sort of like a worst case, most steep line that you could get. But since we have a sigma value of 0.15, you see that this slope is decreased to 15% of what it should be. So the green line is less steep than the magenta line. And again, since we started out with an S of 15, this was the first candidate step size that we examined was basically as S of 15. And again, all we're checking is, did the cost function value at that point decrease from this point by the specified improvement factor? So that's the green line, right? So all you're again checking is, does the blue line fall below the green line? And obviously the answer is no here. So we increment to the next step size. So M now is equal to 1, and this is the situation. So here's now the new step size. So the new alpha candidate is 14.7, and we check again, is the blue underneath the green? No. So we keep going, no, 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 and eventually you see that here the blue does become less than the green, so we exit out of the algorithm. So this is one step of the Armijo rule. So this gets us a step size of, gosh, I can't read this off, I don't know, 8, 9 or something like that. In fact, instead of me guessing, let's just come back and ask it, alpha k. So here, 9.4 is the step size in this case, and let's look at the counter M. So it took 23 steps to find a step size that satisfies the Armijo rule, and basically here we go. This is the step size we're going to take at this iteration using, where is it? These sets of parameters right here. Right? So actually, you know what we can do? Let's just repeat this process. Let me actually comment out this close all. Let's keep all these old figures out. So right now we still have figures for scenario 1, but now let's change this to run scenario 2. So scenario 2 is, if you look at the parameters, it's basically the exact same as before, except the beta value is now not as close to 1, right? So now if we use this beta value of 0.85, again, what this should do with the Armijo rule is within every single sub-iteration, it should take larger changes in step size, right? So again, if we run this, we can now compare the two. And again, let me pull down the appropriate figures. So here's the new figure. And let me see if I can, where was the old figure? Shoot, I have this somewhere. Whoops, where did I stick it? Here. Okay, let me put this on the left, and we'll put this one on the right, just so we can compare. So again, here on the left is scenario number 1. On the right is scenario number 2. And as you can see, the blue, green, and magenta lines are all identical, right? They're the same sets of parameters. And again, S of 15 is also the same. So our first step into the Armijo rule is the same. But now, the only thing that's different is, since in scenario 2, the beta number was not as close to 1, you can see that each time you increment M in the Armijo rule, the step size, or the candidate step size, its delta it jumps, right? It jumps by a larger delta. So in this case, you can see that we're able to find a step size where the actually it's over here. I didn't plot the actual good solution. I just plot the failures. But you can see that a step size over here is going to yield a alpha, which is the blue line is below the green line. So, and again, we can go over here and back to MATLAB. Let me pull up what that alpha value is, alpha k. And again, you see, I think earlier we got 9.4, now you get 9.2. It still satisfies the specified improvement factor, except now instead of taking 23 iterations, it only took 3 iterations to get there, right? So this was faster, and it got us, a situation where the cost function was improved by the specified amount. So let's keep going and playing around with these parameters just so we can get a better feel for this. So let's change this now to scenario number 3 for the Armijo rule. And all we're going to do here is, I want to change the location of the starting point. So instead of starting here at -4, +3, I want to go to this location. And the reason I want to do this is, I know some of you may be following along with the nonlinear programming book from Bert Zekas. I remember I mentioned and I referenced this book earlier. It's an excellent resource. And they draw a figure in that book. In fact, I'll show you it here just for convenience. And as you can see, this cost function looks a little bit more like the behavior we showed up on the board where you have areas of acceptable alpha ranges and areas of unacceptable alpha ranges. If you look at the pictures that we are drawing right here, it's pretty clear that there's one set of unacceptable ranges. That's everything to the right of this. Whoops, oh, sorry, I moved the figure accidentally. Everything to the right of this intersection point is unacceptable, and everything to the left of it is acceptable. So this is a little boring in the sense that there's a clear delineation between these regions. So I want to move the starting point so that we are in a different location and we get a little bit more interesting behavior. So again, let's go ahead and run this, and I'll just show you the differences. Again, maybe what I can do is, let me pull up the figure. Here it is. So now at this new starting location, so in fact, I'll show you the contour plot. So here's this new starting point. And in fact, I think we can also look at the old starting point. You can see here's the old starting point of where we were looking at for scenarios 1 and 2. It's, they look very, very similar. It's just slightly, I moved the starting point ever so slightly, just so that the cost function would have a little bit more interesting variation, as you can see here. So now you can see where there are sections where the blue line is under the green line, and then it goes over the green line, then it goes under the green line, and then it goes over the green line again. So as you can see, again, the whole deal with the Armijo rule is we're just we're monkeying and changing the slope of the green line, and we're looking for areas where the blue line crosses under the green line. So you can see that now we have this section of acceptable step sizes, this region of unacceptable, and then finally over here, a region of acceptable again. And I guess I should have mentioned all these x's here are obviously in an unacceptable region. So this is interesting because now, again, if you look at the S parameter, I guess in this case I chose an S of 7, right? You can kind of see that the initial step size was at 7. So it says still blue is above the green, 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 and then finally, here it goes below the green. So I think it catches probably an alpha, a step size somewhere in this region. So again, let's go and look at this. What did it say did our algorithm get? Yeah, alpha of 4.6, right? So the thing that's interesting is let's take a look at the contour plot, and again, this plot sort of side by side. And again, remember what we were trying to do. Remember when we characterized this cost function, we said that there was actually 5 sort of stationary points or local minima of this function, right? 1, 2, 3, 4, 5 in the center of all these circles, right? And we said we're trying to find the minima down here or up here in these two, right? These were the 2 global minima, right? And as you can see, I think we fell into the correct hole, so to speak, right? It looks like the Armijo rule is starting to get us step sizes which end up in this bottom local minima, right? Which is what we want. But if you look at this, in fact, there's another region of acceptable alphas here, right? Between 0 and I don't know what it looks like, I don't know, 1.8 or something like that, right? So what could potentially happen is if we don't choose the Armijo rule properties or parameters appropriately for this case, for example, like what if we chose an S value of, I don't know, somewhere between, in this picture, I don't know, 2 and 3.75 or something like that, right? You would start here and we would start saying unacceptable, walking back toward here. And what that might correspond to is actually falling into this minima here instead of the one we're looking for. So in fact, let's look at that right now. Let's actually go to Armijo rule. Let's look at this scenario number 4, which as you can see is the same as scenario number 3, except the S value is now less. Instead of starting at 7 and searching backwards, let's start at 3.5 and search backwards. And now, if you run this, you can see that actually that is exactly what happens. So let's see if we can look at all these figures all at once. So here, and then I don't know if I can get the other ones up at the same time. Yeah, here we go. Okay, so the top 2 set of plots are scenario 3 that we looked at earlier, where we started at 7 and started searching backwards and we fell into the right spot. Now, if we start at 3.5, right, and search backwards, we go and find this location as alpha. And that starts yielding us, or starts, nudging the algorithm towards this minima. So again, something to be aware of when you're picking these parameters. You may need to choose different parameters depending on your problem to make sure that you guide the optimizer towards the appropriate minima, right? Now, while we're talking about this, picking the right parameters, right, I know there's that nagging thing in the back of everyone's head of, as we talked about earlier, are you ever going to get out of this while one loop? And I said earlier, mathematically, it should work, right? So let's look at scenario number 5, which is sort of a worst case scenario. So this is, again, we don't really care about where we're starting. It looks like I'm using the same parameters as scenario number 3. But now I'm going to choose a sigma of really darn close to 1. Remember, you don't want this to be exactly equal to 1, right? It has to be in the range of 0 to 1 exclusive. So let's just choose like 0.9999, right? So that is making that improvement factor slope super steep. In fact, we're going to see that the two lines should overlap. The green and the magenta line are going to overlap in this case. And now let's also choose a beta value of really, really close to 1. So again, remember what that means is that with each each sub-iteration of the Armijo rule, the step size is not going to change very much. So this is almost a worst case scenario here. So let me run this, and actually I'll let it start running because we're going to see this takes a little bit longer. If you noticed earlier, the algorithm would almost exit very quickly, within 10, 20 iterations. So now it's running. Okay, it finally decided to finish. Now let me see how many it took. Look, over 1,000 sub-iterations or calls within that while one loop, but it did actually, it exited, right? And in fact, let's look at what the alpha k in this case is. And as expected, what ended up happening is we now have a very, very small step size, right? So again, the picture that goes along with this is over here. In fact, let me just make this larger. Oh gosh, now it's going to take a while to redraw it because there are so many steps. As you can see, right, the magenta and green line are on top of each other right here, and it sure looks like this line is underneath the blue line all the time. So it looks like we're never going to get a case where the blue line is underneath the green line. But again, remember, because we chose it to be a descent direction, eventually, if you zoom in close enough, and gosh, I don't know how many times this is going to take me to kind of zoom in, and boy, MATLAB's, it's running slow here because I did so much extraneous plotting, but we know it exited at some point. So we know that if I kept zooming into this, you'll eventually see the blue line go underneath the green line. So again, I don't know if this is worth our time to keep zooming in and waiting for my computer to update, but I think you get the point, all right? Eventually it will work, and we see that the Armijo rule exits even in these worst case scenarios, but obviously it took a lot of iterations, right? So there are situations where this could take a while to exit. Okay, so I'll tell you what, I'm not going to keep trying to zoom in and dealing with this sluggish behavior. I think that gets us a really good idea and a good feel for what all these parameters are doing. Maybe what we should do now is let this thing rip on the full numerical optimization algorithm and see where the system converges to. All right, so to see this with the entire problem, again, let's just jump over to the right side of my code. And again, this is the same code we were looking at using the constant step size, the diminishing step size, the line minimization step size. So I just added some code and some scenarios for the Armijo rule selection step size. And again, all we had to do was change, or more importantly, add code down here for when we're choosing the step size. Instead of using the constant diminishing or the line minimization, now I add a situation where it's the Armijo rule, and again, all we're doing is I'm literally copy pasting the very simple several lines of the Armijo rule algorithm over here. So it's the exact same thing. So I don't think we need to talk about that too much. The only thing maybe I will talk about is I am storing how many times the cost function or what m is at every step of the algorithm. So effectively, remember, each time you increment m, you evaluate the cost function once. So what we're doing here is I'm going to be able to count how many times did I actually have to evaluate the cost function during the process of this optimization algorithm, okay? So let's go ahead and come back up to the top, and yeah, here, let's execute this first vanilla scenario. So again, let's go ahead and start at, where am I? Scenario 10, that is down here. Here we go. Here's our Armijo rule that we're using with the same steps or same initial guess location we always were looking at. And now what we're going to do is let's again choose an S of 15, sigma of 0.15, beta of 0.98. In fact, I think that's exactly what we chose when we were looking at it over here for executing for a single iteration. Yeah, I think this is this is basically using the parameters of scenario 1 in the single iteration. We're going to use that in the overall scenario, and I'm just going to keep iterating and see if we converge to one of those stationary points, right? So let's go ahead and run this guy, and we'll run it for 10 steps and just see where it goes. And oh shucks, sorry, I probably should have done this down here. Tell you what, let me put in a breakpoint so we can so I can move the figures down here and we can see what's going on. Let me put a pause here. Okay, run. Okay, so here's the picture. In fact, let's dock this in the over to the side so maybe we can see it a little bit more easily. Okay, so again, here's our initial location, and we're free to go ahead and now just step through this. So I'm going to continue, and again, that is the same thing that we got earlier, right? So we see it jumps down here. We found ourselves a step size which satisfied the Armijo rule, so we're going to jump down here. Here's our next point. Now, here's the fascinating thing. In this case, remember that we had an S of, what was it, 15, I think, right here, right? S of 15. So again, all the Armijo rule is going to do is same thing. We're going to look at getting a descent direction here using gradient descent. So if I look at this, I can tell that it's pretty much along this line where I'm trying to draw with my mouse right now, right? So it's going to look in that direction for start all the way at 15. So it's going to start actually all the way over here and then start backtracking until the cost function improvement satisfies the, or is better than the improvement factor, right, that we saw earlier. So actually watch this. At the next step of this algorithm, look at this. Interesting. It actually came up here and found a location that it likes. So now what's also fascinating is if you keep doing this, let's keep running. Come on. Continue. Look at this. It's actually starting to converge to this upper minima, which again, I guess if we look at the performance of the algorithm, right, the cost function value, it starts up high and it comes down low, and it sure looks like it is converging quite nicely to a minima. And again, it is this is a proper global minima. It's maybe just not the one we were expecting. The one we were kind of looking for is this one down here, the one in green that I had highlighted. I think that's what we found in the line minimization technique, was we ended up getting the algorithm to converge down here. But you know, this is basically the same thing, right? The cost function values are the same, so it's getting us the right answer. But this is something that's kind of interesting about these numerical algorithms, is sometimes they get you solutions which might not be intuitive, but at least mathematically they're correct. So it is seeming to do that in this case. Now, if we didn't like this and we wanted to make sure that we sort of ended up down here, I think what we can do is, as you saw, the reason it was able to jump from point number 2 to point number 3 and make that large of a jump is because we allowed it to over in our selection of S, right? We said S was 15, wait a second, sorry. Yeah, well, S was 15, right? So actually, if I go down here to, let me skip scenario 11. Scenario 11 isn't terribly interesting. I think all we were looking at is, well, okay, sorry for jumping. I'll tell you what, let's talk about scenario 11. Scenario 11 is basically the same thing, but as you can see, I'm just changing the beta parameter, so hopefully we're just not going to take as many cost function evaluations. So for example, if I look at what is M data, right, this is effectively at step number 1, we had to evaluate the cost function 23 times in order to get one location. Then on step number 2, it took us 26 cost function evaluations, et cetera, et cetera. So the total sum of this should be the total number of times, sum of, M data. So in this case, for scenario 10, it took us 1,283 cost function evaluations to converge to that upper limit, or to that upper global minima, right? So now in scenario number 11, I'm just going to see if I can reduce that number a little bit. So let me change that up here. Let's go to scenario 11, and we'll run this again. And again, let me go ahead and bring up the plot. So here's the performance. Here's what the plot looks like. So again, we see the same thing. We go from here, we jump down here, and then we jump up to the top minima. And then it's got a little bit different behavior here, but at the end of the day, it still finds this same global minima. But now, if we look at M data, you see that at each sub-iteration of the Armijo rule, it takes less and less steps. So actually, again, looking at this, is now only 232. So I think what was the earlier number? Something like 1,293 or something like that. So look at that. It only took about 18% of the number of function evaluations. So it was much more economical in finding that that minima, right? Okay, so now let's talk about scenario number 12. Okay, so let's scroll down here and let's take a look at what's going on with scenario number 12. Okay, so this is the case where I'm going to basically take the exact same parameters of scenario 11, but I am going to handicap the distance s. So instead of allowing you to search 15 units in front of the direction, I'm only going to allow you to search 10 units in front. So that is hopefully going to avoid this problem, or I guess I don't know if you want to call it a problem, but it will avoid this phenomena of allowing it to jump from down here all the way to up here. With a step. So let's go ahead and run scenario 12. Actually, I think I changed it already. So let me go ahead and, in fact, let me put a breakpoint in again down here so I can move the figure onto the screen so we can see it easily. All right, let me put a breakpoint here. Hit F5 to run this. And again, let's go ahead and dock the figure. And now let's go and run. And as you can see, yeah, the first step, we jump down here. Now this next step, if you continue, look at that. It stopped here. And that's because we didn't allow it to search all the way up here. It had to stop within 10 units. And basically, it's starting to now, you can see, converge to this bottom minima, as we discussed earlier. So again, we still get it falling into one of these global minima where I think the cost function value is about 36.4, I think is the actual minima. That's exactly what we're seeming to nail. It just happens to find the other minima, right? Okay, so this is great. So we're seeing that we can really tune how the optimization algorithm performs by basically changing these parameters of the Armijo rule. So let's look at scenario 13, okay? So scenario 13 is, again, another different variation on the theme. And now we are going to just change the initial condition and show that we can still find that, that bottom global minima. So let's do that here. So again, scenario 13, in fact, again, this is not terribly interesting. So let's go ahead and run this and we'll take a look. So again, here's the performance. Here's the actual results. And as you can see, it converges nicely. But now with this initial condition, we are also in sort of that danger zone that we looked at earlier, in the sense that you can see that in order to get to this minima, it had to cross over this other minima, right? It had to cross over this local minima on its way to finding the global minima. So in this case, I think we were lucky, so to speak, by looking at these parameters with S of 7, right? Actually, this is the case we were looking at with the single iteration, right? Where with an S of 7, you give it enough leeway to search that it can find this global minima. But if we were to handicap that here, if we tell it not to search so far, we'll get stuck in this local minima instead of finding the global minima. So in fact, we can see that with scenario 14. If we go ahead and change this to scenario number 14 and rerun again, right? Let me show you that here's the performance and here's the results. So as you can clearly see, we fall into the local minima with the Armijo rule, and we do not get down to this global minima function value. So again, this is a little bit interesting. That being said, let's go back to scenario 13, because scenario 13 seemed to get us what we were looking for, okay? And what I do want to point out is that, yes, this gets us a location that we're interested in, so it looks like this solved the problem appropriately. And the nice thing about this is, again, if you look at the number of function evaluations it took, you know, I don't know, 837 cost function evaluations in order to perform the algorithm. Now, if you compare that with, if you remember our line minimization that we looked at in the previous discussion, right? We said that this also finds that appropriate location, but if you think about this long enough, what we're doing with line minimization is, you remember we discussed that in order to practically do line minimization, you're doing something like this, right? You're basically slicing up the alpha steps between 0 and s, right, your maximum value, with some number of alphas. So again, let me run the line minimization, and line minimization, you see here, we nailed it in only 5 steps, right? It ended up finding this bottom global minima. It did this on first appearance, it looks like it's very efficient, right? It only took 5 steps of the algorithm to get here. But at each step of that algorithm, what you're doing is you have to evaluate the cost function at all of these alpha values. So in this case, that is 1,500. I'm doing 1,500 cost function evaluations for one step of the algorithm. So if it took 5 steps to get to that global minima, and at each one of those I'm doing 1,500 evaluations, I'm evaluating the cost function 7,500 times in order to generate this result and converge to this solution via line minimization. And we saw that Armijo rule got it to us in, oh gosh, I already forgot the number. It was like 870-ish or something like that. So look at that, 10%, it's 90% faster, it only takes 10% of the time, right, to get to there. Even though it took more steps, it took only 10% of the time in terms of how the economy associated with evaluating the cost function. So as you can see, the Armijo rule is much better in terms of I guess economy. So it might take more steps, but it will get there faster than doing something like line minimization. Okay, I think that's enough talking. Why don't we go back to the board and wrap this up? All right, so there you have it. One more tool in your tool chest of numerical optimization routine algorithms, and specifically how to choose the step size via the Armijo rule. So as you can see, it might appear complicated on first blush, but actually to implement it is not that bad, right? You can code this up in just a couple of lines of code, and you end up with a technique which provides some very nice guarantees about convergence and some very nice behavior. And it saves us from evaluating the cost function an excessive number of times, and really allows us to zero in on step sizes that guarantee a specific amount of cost function improvement with each step of the algorithm. So with that being said, I think this is probably a great spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. Surprisingly, if you just scroll a little ways down and click on that subscribe button, it really does help me continue making these videos. Another way that you can support the channel is via Patreon, and the nice thing about that technique is that 100% of the proceeds that the channel receives via Patreon are going to be directed towards K through 12 science, engineering, and adventures for K through 12 kids and young adults. So I think this is probably a good spot to sign off. Remember, the new videos come out every Monday, so I hope I'll catch you at one of those and we can all learn something new together. All right, so until then, I'll talk to you. Bye.